Chemisters, this is Mrs. Vanderlei bringing you another blank wall. This is Chapter 6, Section 9, Part 2. So we left off calculating the heats of formation or the heats of the reaction based on the heats of formation. And I had told you to go out or go find your chart with all those numbers on it. I hope you still have it. I also said that this equation is found in your equation sheet. You may have said, I don't see it here. Well, it's right here. Here's the equation that you probably have in your equation sheet. So what does this say? To calculate the heat of reaction in its standard state, the little knot there, subtract the enthalpies of formation of the reactants multiplied by their coefficients are right here from the enthalpies of the formation of the products multiplied by their stoichiometric coefficients. So a few things here. What does this funky looking Greek letter stand for? That's your Greek letter sigma, which means summation. So you're going to add up all the heats of formation of your products minus adding up all the heats of formation of your reactants. Okay, so what are we going to do here? Well, we're going to use the same equation that we had before. And so let's see if we can't calculate this methane combustion reaction. So how do I find the delta H of this reaction? Okay, well, I'm going to start over here again. Okay, always write down your equation. You know that, don't you? So notice what I do this time. I take the heat of the formation, I start off over here again, take the heat of the formation of carbon dioxide, I only got one of them, plus the heat of formation of your liquid water, I got two of them. And this whole term right here, add up first. Then subtract your heat of formations of your reactants. Here's your methane, I only got one of them, and your two of your oxygen. I also want to bring back another idea real quick. How did we start this section? We said, what does the delta and delta H mean? It means final minus initial, just like delta T means final temperature minus initial. And that's what we're doing right here, isn't it? We're taking the final, all right, these are my products, these are the finals, minus the initials. Doesn't that make sense? Pretty clever, isn't it? So now I'm going to put in all these numbers here, okay? You may be saying, holy cow. So here's my 1 mole of negative 393.5 kilojoules per mole plus 2 moles times negative 248 kilojoules per mole. This is my carbon dioxide and this is my 2 water liquids. Add those two together, subtract 1 mole times negative 74.6 plus 2 moles times 0. And what do you notice here, folks? What happens to my unit moles? Don't moles cancel? Don't moles cancel? Oops, sorry. Nope, don't do that. Try it again. Don't moles cancel? And here. So what unit is the only one left? It's kilojoules, isn't it? Okay, so I'm ready to do the math. What's negative 393 plus 2 times negative 241 plus 74.6? Oops, I'm back here. You get this. Do you recognize that number? Isn't it the same one as before? Yes, it is. Okay, let's try the next one. Number 49. Use the standard enthalpies of formation to determine the delta H of the reaction for this one. I want you to pause this. I really mean it. Do it and see how you do. Pause it. That means you. Now. Okay, how'd you do? So did you remember products minus reactants? I hope so. So let's scroll down here. Here's my formula. Summation, adding up all my products, including their coefficients, minus summation, add up all the reactants, including their coefficients. So I have 4 NOs plus 6 H2Os. Notice this one's a gas. You're not going to use that negative 241, are you? So add them up minus, all right, your reactants, your initial, all right? And then I have a whole bunch of numbers in here, all right? Adding them up minus adding them up. Notice that oxygen 0, all right? Notice that oxygen is 0. That makes life pretty easy, doesn't it? And I add them up, I get negative 902.0 kilojoules, okay? So now what? Let's do problem number 40. Once again, what's happening here? Oh, there's a little twist, isn't there? I left something out, didn't I? Oh, I see what I did. Hang on, I'll fix it. Be right back. Bye. Okay, had a little formatting problem, but we're back. Okay, so now what? It says the standard enthalpy of combustion of ethane gas is negative 1411.1 kilojoules per mole. Give the following standard enthalpies of formation. Calculate the heat of formation for ethane. Why don't you go ahead and write down its formula or its equation right now? You can do it. Come back when you're done. All right, is this the equation you came up with? I sure hope so. So what's happening here? They're telling you the heat of the reaction is, they're giving you this number right here. That's that negative, whatever, the negative 1411.1 kilojoules. They gave you that. And now, what's it equal to? Well, look at your reactants, 2 carbon dioxides and 2 waters. Add those two together, minus, all right, the ethene plus 3 oxygens, okay? So what's wrong? They gave you carbon dioxide, they gave you water, they didn't give you oxygen. Isn't that strange? Why do you think they didn't give you oxygen? Because what is its value? It is 0, okay? So a lot of times they won't give you your elements in their standard states because they're going to be zeros. So they're asking you to calculate this. It's not on your chart, is it? Oh, no. So you need to calculate. Well, they gave you this, so it shouldn't be any problem, okay? So what's my next step? All right, plugging in some values. Oh, looks like I'm off a little bit again with my spacing. Oh, well, sorry about that. So I end up with 2 times negative 393.5. They gave me that. 2 times negative 2. Whoa, they didn't give me that. Hang on. Okay, I went ahead and put the right value in here. See how easy it is to make a mistake there? I was in a groove. I was using that same number, and boy, I was being careless, wasn't I? So anyway, I have the right number in here. So how do I solve for this? Well, this is still the same number, isn't it? And I put 2 times negative 393.5 plus 2 times negative 285.8. Added that up, and I got negative 1358.6 using my new value. Why is it minus delta H then? Well, it's 1 times this plus 0, which is still negative delta H of the ethene, isn't it? I should scroll this down a little bit so you can see a little bit. There we go. And now what? Well, how do I solve for delta H? I'm going to add 1358.6 to both sides. And I got, bring it up here, this. And now what? Well, get rid of all the negatives, and I got 52.5 kilojoules as the ethane, heat of formation for ethane. I hope you got the same number. Check my work and tell me tomorrow if I don't, okay? Let's go ahead and you do the next problem. I think you can. Go for it. So it says, using the enthalpies of formation, calculate the standard change in the enthalpy for thermite. Go ahead and do that right now and see what you get. Okay, let's see how you did. I hope you wrote down your formula to start with. Wouldn't that be nice? All right, and then I plugged in the value. So here's your aluminum oxide, here's your iron, minus your aluminum here and your iron 3 oxide. Then what? I plugged in the values here. Notice iron and aluminum are both zeros. Isn't that wonderful? So really, what are you boiling down to? You're getting 1 mole of negative, 1676 plus 0, which is negative 1676, minus a negative 826. So what happens? You take negative 1676 minus a negative. I think you get a positive, don't you? So what's negative 1676 plus 826? I got negative 850 kilojoules. I hope you did too. This isn't too bad, is it? All right, so this is like a word problem, all right? So what do we need to do? City of 100,000 people uses a lot of kilojoule of energy per day. Suppose all that energy comes from the combustion of liquid octane to form gaseous water and gaseous carbon dioxide. Kind of unrealistic, don't you think? Use the standard enthalpies of formation to calculate heat reaction for the combustion of octane, and then determine should be how, not who, many kilograms of octane will be necessary to provide this amount of energy. So go ahead and calculate the heat of reaction and then factor label, just like what we did when we talked about stoichiometry. I think that was 6.7. So go ahead and do that. Come back when you're done and see how you did. Yes, pause this. Do it on your own first. Okay, welcome back. Let's see how you did. Well, as you know, you're supposed to write down the formula. Oh, the equation, and then the formula. Products minus reactants. Hopefully you got that. So 16 carbon dioxides, 18 liquid waters, minus 2 octanes and 25 oxygens. I bet you know what those oxygens are, don't you? All right, so then I plugged in my values. I hope you got the right ones, or I hope I got the right ones, okay? So 16 times negative this was 18 times negative that, minus 2 times negative 249. So this is actually about a positive 500 plus 0. So this is going to be a big negative number, isn't it? That's what I got. I'm hoping you did the same thing, all right? But I'm not done yet. What can I do with this value? I can stick it right here, can't I? All right, because this is now part of the equation, it's part of the products. And that's how I kind of use that stoichiometry. So what does this 10,148 mean? For every 2 moles of octane, I get 10,000 kilojoules of energy. For every 25 moles of oxygen, I get 10,000 kilojoules of energy. Do you get the point? So does that help you factor label? I hope so, because what can you do now? How many kilograms? I assumed it was per day. Okay, it didn't say so, but that was my assumption. So in one day, they give off negative a lot of kilojoules of energy. And then I put kilojoules on the bottom, that negative 10,148 for every what? 2 moles. This is your stoichiometry again. And then 1 mole of octane is 114.26 grams. And then, of course, they want kilograms, of course. So I put 1,000 grams on the bottom, 1 kilogram on top. And that's how many, you're talking about 2.3 million kilograms of octane every day to fuel the energy for the city. That's crazy. Let's do one more problem. All right, so it says the chemical hand warmers described in the very opening produces heat when they're removed from their airtight plastic wrappers. Recall they utilize the oxidation of iron to form iron oxide according to the reaction. So how much, or calculate the delta H reaction. Just think about it before you do. Is your delta H be positive or negative if it's a hand warmer? Think about that. And calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. Go ahead and do this. Pause this. Come back when you're done. Yes, I mean you. Okay, let's see how you did. Okay, products minus reactants. Hope you're getting good at that. So I have 2 moles of the iron 3 oxide minus this whole quantity of 4 moles of iron and 3 moles of oxygen. Oh, what are these two values right here? They're both zeros, aren't they? Why are they both zeros? Because they're both elements in their standard state. So this is written almost as a heat of formation. If I divide everything by 2, then I would have had that. If it had been 2 FEs and 3 halves oxygen makes 1 Fe2O3. All right, but because it's not, I had to multiply it by 2 and get a big number here, right? What I get? There we go, 1652. But I'm not done yet, am I? I still need to decide how much heat is produced from the hand warmer containing 15 grams, periodic table. Let me scroll up. So if I had 4 moles of oxygen, 4 moles of iron, I meant right up here, man, that would be a lot of heat. That is negative 1652 kilojoules of heat. Ow, 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 that would burn me, okay? So the hand warmer is not going to use 4 moles of iron. Holy cow, it's over 200 grams, isn't it? So how much are they going to use? Let's use 15 grams, all right? Stop that. So I put grams on the bottom, and what goes on the top? 1 mole. But wait a minute, I have 4 moles of iron giving off negative 1652 to give me a much more reasonable negative 111 kilojoules. That probably won't burn me. Remember, it's kind of the same idea. Would you stick your hand in the beaker of boiling water? Of course not, Mrs. Vanderlei. But might you put a drop of hot water or boiling water on your hand? Yes. Why? Because I'm using less. It's less heat. Okay, hopefully that makes sense to you. And that concludes chapter 6. Okay, don't wait to be great. Take care. Bye-bye.